Welcome to Maths with Bob. Today we're looking at the discriminant and how we use it. Now the first thing I guess is, where does this discriminant come from? Well, if you actually have a look, this is actually taken out of Word. This is you can see this is the quadratic formula. Okay, and obviously this is, you can see straight away that okay, if you have a look at this bit here, okay, and have a quick look underneath the square root sign under here, you can see, hello, these pieces are in fact the same, and that's where the delta, or the discriminant if you like, shows up in the quadratic formula. And because it's either can be positive 0 or negative, that would indicate that the roots of a quadratic equation will basically change in nature, I guess. So the first thing to realize is the discriminant comes from quadratic equations and quadratic functions themselves. Okay, and as we all know, hopefully ax squared plus bx plus c. Okay, if I make that equal to 0, this is now a quadratic equation. And if I, let's have a quick look, if I change this to, say, equals y, that becomes a quadratic function, and its graph looks like a parabola. Okay, so the first thing is, what is the effect of the changing values of the delta? Okay, so let's actually have a quick look at the changing values of the delta. Okay, so first of all, we need to have a look at the situations. Now there's, I'll just quickly draw them up. Okay, here we have, let's actually draw them all and extend this diagram a little bit. Okay, and we can also have them basically like this. Supposed to touch here. Okay, now, okay, so we have a situation where we can have parabolas, okay, in varying situations. You can see in the number plane. A couple of them being given special names. Let's go over this one here. This one, I'm just going over in purple, is called a positive definite. Okay, and the one I'm going over here down in purple down the diagram below, that one is called a negative definite. So we can call this one here a positive definite. Oh, it's definitely positive, I guess you could also say. And this other one here is called a negative definite. Okay, so you can see here the other two, well, let's have a quick look at this one. This one actually has a double root, you might say, and at the same being the same value, and the one across actually has two roots. Okay, you could say that one has one root with that purple dot there. Okay, so how are we going to determine the position of the parabolas, if you like, by this discriminant? Well, the first thing is that, okay, let's have a look. Here, obviously, A would have to be positive in all these cases. So this is the A being positive case, which means, okay, they are sort of concave up, if you like, and down here, A is negative. So the first thing to realize, I guess, is that if a quadratic expression has a negative x squared value, or the coefficient of the x squared value is negative, it's upside down, or some people say it's sad. If the coefficient of the x squared term is positive, okay, that is the A value, which is the coefficient of the x squared value, which is positive, then they're happy curves, or concave up, you might say as well. But basically, okay, what about the deltas? Well, let's have a quick look. The delta of this one is in fact less than 0, the delta of this one is equal to 0, and the delta of this one is actually greater than 0. Okay, so let's have a look down here. Okay, the delta of this one below here, okay, is less than 0. The delta of this one is equal to 0, and the delta of this one, okay, is greater than 0. So a few things hopefully are starting to take shape in that if delta is positive, there are two roots. Delta 0, there is actually one root, okay, sometimes called a double root. And if delta is negative, okay, there are no roots. So how do I actually show that a particular quadratic function is positive for all values of x? First of all, I need to show that if A is positive, then delta is negative. Okay, how would I show a quadratic function is negative for all values of x? Well, A would need to be negative and delta would need to be negative. Okay, so these are some ways we can use to show things are completely positive or negative. Okay, so just before we go on, let's actually just summarize this, I think, on the side here. So first thing is, okay, if delta is less than 0, there are no roots to the quadratic equation, or if you like, the parabola doesn't cross the x-axis, or its y value equaling 0 never exists, I guess you could say. If delta is equal to 0, okay, the parabola will come down. You can see here the middle ones, they sit at that purple and black dot, and we have a double root, or just some people say just one root, a repeated root if you like. Okay, and if delta is actually basically greater than 0, this is the third case when we have two roots. Okay, so basically that's a quick summary. Okay, so delta is less than 0, the parabola never crosses the x-axis, i.e. y never gets down to a y value of 0, or up to a y value of 0 for that matter. Okay, if it's a negative definite. If delta is equal to 0, then obviously the parabola is actually sitting on the x-axis at one particular spot, and if delta is positive, we are having a situation where the parabola is cutting the x-axis at two spots, giving us two roots. Okay. Well, okay, here we have a situation where we were asked to find the equation of two lines that contain a point, 1, 3, and are tangents to the line y equals minus 2x plus 5. Now, sometimes I like to just draw a little drawing just to see what this would look like. So basically we have a situation where we have some sort of parabola, and we have a point, this point being 1, 3, and it's actually sending out some tangents, okay, to this particular parabola. Now, at this stage we're not asked to find the points of intersection, okay, this one here, we're not asked to find those, we're just asked to find the equations of these two lines. Now, how are we going to do this? Well, the first thing is we're going to actually have a look at what's the general equation of a line. Well, we know y equals, say, mx plus b, and we also know that y is equal to x squared minus 2x plus 5. So this hopefully would suggest that we just basically reform a new equation, that mx plus b is equal to x squared minus 2x plus 5. Put everything over one side, so x squared minus 2x minus mx, okay, so it's plus 5 minus b, and that should equal 0. Okay, so we normally also factor out, so rewrite this, try and get the coefficient, so it's going to be what, minus m plus 2 lots of x plus and then 5 minus b equals 0. Okay, so once we've got this situation, okay, we then think to ourselves, okay, it's going to be tangential to it. Okay, so it has to touch it at one spot, or it has to have a single root or a repeated root, and hopefully this will might tell us that we're going to look for a delta equals 0 situation. Okay, if we see the word tangent, okay, we hopefully will sort of remember that delta is equal to 0. Then in fact the x-axis, remember, was a tangent to the actual parabola. So this is the situation we need to apply here in this case, and we now need to find well, if you like, the discriminant of our expression down here. So let's have a look at what delta would be. Now, you can see here it's going to be what? Well, b squared minus 4ac. Let's just rewrite it. Okay, is equal to, in this case, minus m plus 2 all squared, minus 4, okay, times a, which is 1, and c, which is, let's put that in brackets, 5 minus b, so we don't forget to multiply it out. Okay, so we need to actually work out what the delta is. Okay, so let's just try and work out what this delta is. Okay, well, I've just worked out, I've expanded it out, b squared minus 4ac. Okay, now, the only problem is, this is not really a quadratic in one variable, it's got two variables, so we then have to go back and think to ourselves, okay, well, what y equals mx plus b, okay, and we know that the point 1, 3 lies on this line, okay, so x is 1, y is 3, therefore 3 would equal 1x plus b. So this is going to now allow us to do a substitution for, or 1x, oops, sorry, that shouldn't be, it should be just an m there. That's m here. Okay. So we need to now basically look at the quadratic form for the delta. And now we can either change it or, let's have a look, we've got m's or b's, so we can make it in terms of b's or m's. I think I'll just make it in terms of m's. So what is b? B is going to be equal to, you can see here, just 3 minus m. So we need to substitute this expression, okay, this one here. Obviously that needs to go into here for lots of it, okay, you can see here. So we're going to substitute the b value in there and then get the delta in just in terms of one variable, m. So okay, let's try that. Okay, so let's have a look. So delta worked out to be what? M squared plus 4m plus, now plus 4 minus, okay, so let's actually just write that as minus 16 plus 4 lots of b, which is just 3 minus m. And you can see here that would be 3 fours at 12. Okay, so it's going to be what? M squared plus 4m minus 16 plus 12 minus 4m. And you can see one of the interesting things happens here, that in fact the 4m's would actually cancel, leaving us with just what? M squared minus 4. And hopefully, okay, and if we set that to 0, we can see that that's just a m plus 2m minus 2. Therefore, you can see here that m would equal basically plus or minus 2. Okay, so we are nearly there. Okay, so we need the two lines now. So what we do is we back substitute these values. Okay, so let's actually have a quick look. What do we do? Well, let's go over to the side here. So if we know that y is equal to mx plus b, and we know that, say, m is equal to 2. So m is equal to 2. We know that b is equal to 3 minus 2, which as you can see here is just 1. So therefore, one of the lines would be y is equal to 2x plus 1. Okay, let's have a look at m is equal to minus 2. Okay, then b would equal to, well, b is equal to 3 minus 2. You can see that's just 5. Okay, and the other line, therefore the other line would be y is equal to minus 2x plus 5. Okay, so we now have the two lines. Okay, so the two lines you can see here, okay, will be this one here and this one here. So they'll be our two lines. Okay, well, thank you for watching. We'll try some more problems shortly. Bye for now.